Gaussian surface. Now if you see in our Gaussian surface, what is the charge present inside? It's Q. So I'll write here Q. Q by epsilon naught. So we'll get the value of E. E is equal to Q by 4 pi epsilon naught R square. We've got the answer. Now you tell me, did you understand this one?
Yes.
Yes, sir.
Okay, easy. So we'll now proceed to the next thing. Now I'll give you one question. If we try to find the electric field inside a hollow sphere, hollow charged sphere. Now let me just write what is the question statement. This is my sphere. Consider this as a sphere which is like a hollow ball. You can consider it as hollow ball. Nothing inside. And the charge Q is distributed all over its surface. Now the question is, you need to find out the electric field at 3 points. One point is A, where R is greater than capital R, where capital R is the radius of this sphere. And the second point is on the surface B, where R is equal to capital R. And the third point is at a point inside C, where R is less than capital R. Now you tell me, can you apply the Gauss law to find out the electric field at these 3 points? Manas?
No. R less than R. Hollow, no, sir. If capital like small r is less than capital R, then it will be 0.
Why?
Because inside there is no matter, and then you're stretching it.
No matter not. Charge.
Charge. There is no charge. All the charge is getting shifted to the surface.
No, so, that is not shifted.
Not shifted as a
no. Don't tell me that concept, because that concept applies to the conductor only.
Okay, so there is no charge in the middle, so it is 0.
Correct.
And if it is equal to R, then it is going to be KQ by R, capital R square. And if it is greater than R, then it will be KQ by small r square.
KQ by small r square.
Yes.
This how did you calculate? Can you explain?
Sir, by using what we got for the point charge.
Acha, the same way you have constructed the Gaussian surface, na?
Yes, sir.
Dharni, you understood, or you want me to do it?
Sir, once can you explain?
Okay, wait, I'll explain. See, yes, if you are taking this part, this outside one, for this outside one, for the A point, what we'll do, we'll just, because we have to find the electric field at A, we will just construct a Gaussian surface here. It will be big, like this. Okay, like this we have constructed the Gaussian surface. And here, why we have constructed? Because we need to find out the electric field at this radius. Now E dot ds will be equal to Q inside by epsilon naught. Now our focus is this Gaussian sphere, Gaussian surface. E is always constant to this because at every point electric field will be same because it is at same distance from the center. So we will take electric field outside. So it will be surface integral ds. It will be, and now what is the charge inside this Gaussian surface? It will be capital Q by epsilon naught. So surface integral ds will be what? It will be the surface area of this Gaussian surface that we have taken. So it will be E into 4 pi small r square. That will be equal to Q by epsilon naught. So E will be equal to Q by 4 pi epsilon naught small r square. He has told it K because we represent 1 by 4 pi epsilon naught as K. So then it will become KQ by small r square. Understood this one?
Yes, sir.
Yes.
Okay. Okay, now if we take the second case on the surface, R is equal to capital R. The Gaussian, since we have to find out the electric field at the surface, we have to create our Gaussian surface at that point only, at the surface only. So now our blue one will be the Gaussian surface. Here everything will be same. Surface integral E dot ds is equal to Q inside by epsilon naught. We are creating the Gaussian surface just outside this shell, just outside. So that almost the radius is equal to capital R. So in the same way, this electric field will come out, this E will come outside because it is constant. Surface integral ds will become equal to 4 pi capital R square, that I'll write later. Q inside will be Q by epsilon naught. So E into 4 pi capital R square is equal to Q by epsilon naught. Now E is equal to this Q by 4 pi epsilon naught into capital R square, that we can write as K capital Q by R square. Understood?
Yes, sir.
Now we take the third case. The third case is inside. Now here, what is the case? See, we have to find out the electric field at C. But the problem is, we can always draw a Gaussian surface here. But the thing we have to look at here is, if we draw the Gaussian surface, everything will be same. In surface integral E dot ds will be E into, E will come outside, it will become ds is equal to Q inside by epsilon naught. But now if you see here, E into 4 pi r square it will be, but inside this Gaussian surface there is no charge present. There is no charge. The only charge was present on the shell, which is outside our Gaussian sphere. But we have to take all the charges which are present inside our Gaussian surface. So that's why, because there is no charge, this Q inside will become 0. So it will be 0 by epsilon naught. So that's why the electric field will be equal to 0 inside this. Now tell me, understood or not?
Yes, sir.
Yes.
Okay, very good. Now my question will be, in this particular case, can you draw the graph of electric field versus small r? Try to draw the graph and then tell me. If you want, you can annotate on the screen also. No Manas, wrong. Danny, can you draw? You are also correct, but you are correct, but you have done some mistake. Achha, this is minus, no? No, minus. No, minus. Still it's wrong.
Sir, I think it will be an increasing graph.
No, it won't be increasing. It will be decreasing only. It will be decreasing only. Why? Because actually he has drawn up very correct, but there was only one mistake. It won't be increasing. Why? See, let me just write. Electric field from small r less than capital R, when it is radius less than capital R, the value is 0. Now he is correct. Now it will be k cube by capital R square. E from R greater than capital R, it will be k cube by small r square.
Sir, I was trying to get that vertical line what I drew into a dotted line, but dotted line was not there here. That was whatever I drew. That यहाँ से यहाँ तक, from here to here. What I drew was a dotted line, but dotted line is not available.
Then it's okay. Then correct. Then you are correct. See Dharani, what he's trying to say, na, graph will be in this way. Graph will actually start from this point. What is this point? R is equal to capital R. Why? See, if you see, focus on this one. If you see, from when you're going from 0 to center, when you're going from center to the capital R, there is no charge. See this diagram. From center to the capital R, there is no charge inside. So at every point from center to the surface, there will be no electric field. So when electric field is not there, why we will represent any electric field here? There will be no electric field from 0 to capital R, this point. Now after R, at capital R means at the surface, the value I am starting from here. The electric field I am starting from here. Why? Because at surface, small r is equal to capital R, the value of the electric field is the value of the electric field is this. This value is k q by capital R square.
Yes, sir.
Now when we move forward, after this, when we are getting away from capital R, this electric field is getting inversely proportional to small r square. When we have, now this will be a concept for you in the future. It will help you a lot in future to draw the graph. Whenever you have something like a is like x is y is inversely proportional to x, or inversely proportional to x square, or is inversely proportional to x power n. In all these cases, your graph will be this way only, like this. You must have done this in your chemistry, class 11. PV is equal to constant, that graph is there now.
Yes, sir.
P is inversely proportional to the volume minus, that's why this graph.
Yes, sir.
Now if you see here, this electric field is, after this capital R, this electric field is getting inversely proportional to this r square. So the graph will be in this way. It won't touch the x-axis, but it will move like this. That's why he was drawing the graph like that. Understood?
Yes, sir.
Achha, now let me give you one more thing. Now we'll come to the next part. Actually, I like this feature of the Zoom where you can annotate. Later, when you will become comfortable, I'll suggest you to buy one pen tablet. When you will be studying, if I ask you some question, you can just solve on the screen and then show me. Now I'll give you one more thing. Electric field inside a solid sphere. Manas, can you do this? The question. Let me just explain you what is the question statement. This is our sphere. This is a solid one. Now, what is given to us? There is a charge Q which is uniformly distributed inside. Okay, understood? Now, in this particular case, we have to again find out the electric field at 3 points. One point is this, R greater than capital R, A. The other point is again the surface, where B, where R is equal to capital R. And the third point is again inside, R less than capital R. Now tell me, can you do this one?
Until can I have 1 minute of time?
You can have more than 1 minute if you want, you can take. And if you get any doubt in between, you can ask me. Dani, if you have got any answer, you can just tell me, sir, I have got the answer.
Sir, for that outside point, it is going to be kq by small r square.
Okay, correct.
And inside, inside, does it contain a charge?
Yes, it's uniformly distributed.
So it is going to be kq by kq by small r square, like small r which is there.
Just tell me your answer. I'll tell later. I'll tell whether it is wrong or correct.
I
KQ.
think it is kq by capital R minus small r whole square.
No, wrong.
And for surface, you can take any one of the formula kq by capital R square.
Your first two results are correct, but your third one is wrong. See, let me tell you. Then just look at. Did you solve any of those results?
Sir, I got the first one.
Okay, very good. So, do you want me to solve first one? Second one?
Yeah, sir.
Second one also you will be getting. So no need to solve A and B, na?
Yes, sir.
Okay, then we'll go for the third one direct. So if we go for the third one, what is the problem, na? The problem is, according to our process, first we have to draw Gaussian surface. We have drawn it. It's okay. Now what the problem is, when we apply the Gauss law, we have to get this E dot ds is okay, but we have to get q inside. That is the problem actually, and it is this one q inside where this Manas is doing mistake. Yes, na? See, Manas, when you try to calculate the q inside, how do you do it? How you do it? I'll tell you it. See, capital Q, this if you see this capital Q charge, this is actually totally distributed in this volume. So if you see, for the 4 by 3 pi r cube volume, the charge is capital Q. Now what is the volume of this Gaussian surface that we have constructed? It's 4 by 3 pi small r cube. Then for the 4 by 3 pi small r cube, how much charge will be there? Capital Q by 4 by 3 pi capital R cube into 4 by 3 pi small r cube. So this will be our Q inside.
So even if we cut out 4 by 3 pi and 4 by 3 pi, okay, that will be the inside charge. So it is going to be k q r cube by small r cube by capital R cube.
No, still you are wrong. I'll tell you there is one more method to find. See, in your classes, na, if you are suppose studying in your CBSE classes, in your schools, they will tell you this one in another way. They will calculate the volumetric charge density.
Yes, sir. So they'll give it as inside point. They'll give it as rho into small r by 3 epsilon naught.
No. Let's first understand what is volumetric charge density. It's the total charge divided by volume. Total volume means actually it is charge per unit volume. In this case, it will be capital Q by 4 by 3 pi capital R cube, because the volume of the sphere is 4 by 3 pi capital R cube. If you need to find out the charge of this Gaussian sphere, it will be this rho into 4 by 3 pi small r cube, same thing. Okay, either way you can do. Now before proceeding, let me just confirm whether you understood this or not. Dharni, you understood?
Sir, once can you explain the volumetric charge density again?
See, what is volumetric charge density? Na? Volumetric charge density is defined as charge present per unit volume. See, actually this total charge is present inside the volume of the sphere, correct? Uniformly. Now,
Yes, sir.
now if you try to calculate the charge per unit volume, that is, which is volumetric charge density, means you are trying to calculate charge which is present in 1 meter cube volume. So you will just divide the total charge with the total volume of the sphere. So you will get the volumetric charge density.
Yes, sir.
And now, since you have got the charge which is present inside the 1 meter cube volume, 1 unit volume, so if you need to find out the charge which is present in this 4 by 3 pi r cube area volume, you will just multiply this volumetric charge density with 4 by 3 pi r cube. You will get the charge inside.
Okay, sir.
Okay. Now see Manas. Now this is Q inside you have got, so it will be rho into capital Q into small r cube by capital R cube into epsilon naught. E will come outside as usual, and this surface integral ds will become 4 pi small r square Now this r square and this will get cancelled. E value will be q small r by 4 pi epsilon naught capital R cube. So the answer will not be this. It will be kq small r by capital R cube.
Okay.
There are two ways. Either you can do by this method. If you are comfortable in this, you can do by this way, or you can do by this volumetric charge density. Both are fine. Now I will ask you to draw the graph between electric field versus R. Wait. You need to draw the graph of E versus R for this case. If you know, just annotate it on the screen. What is this?
No. That was human, technical error.
Human error.
Technical error. Oops, like that.
Correct, very good. This is the graph. Let me explain it in detail. Then we will end the class after this. See, the graph will be this way, like minus is drawn, and this point will be small r is equal to capital R. After this, the graph will go like this. Why, I will explain you. See, when you are going from R to capital R, the thing that you have to follow is this one. Here, electric field is actually k cube capital small r by capital R cube, and these things are constant. K is constant, Q is constant, capital R cube is constant. So actually, E is becoming directly proportional to R. This is only up to capital R. So this graph.
Yeah. After it reaches capital R, then it will decrease exponentially.
So because after this point, understood na Dharani?
Yes, sir.
After this, what will happen? At capital R, the value will be obviously this one. This point will be your k capital Q by capital R square only. After this, what will happen? Again, the same graph. Electric field is equal to capital Q by small r square. So E is getting inversely proportional to R square. So again, the same graph will be in this as we have done in the previous case, like this. So that's why the graph is this way. Okay, I think you have understood.
Okay, so
Then I'll end the class.
Sir,
Then,
1 minute. Sir, why didn't we put the dotted line for the first one?
Dotted line. Acha. See the dotted, if we take the case when we do the dotted line, acha, this dotted line. No. This dotted line was only to show you.
No,
This,
sir, I'm asking about the first one. E is equal to KQR by capital RQ. But like, how will we get that line?
how we will get that curve?
Yes, sir.
So for that you need to understand. You need to have the idea of this one. The graph of y is equal to mx. Do you remember what is the graph of y is equal to mx?
Yes, sir.
If y is this, x is this, the graph of y is equal to mx is this.
Yes, sir.
It means what? The slope of this line is m, which is tan theta. Now in the same way, if you see this one, for this one, this point, electric field is actually like this: kq by capital RQ into small r,
Yes, sir.
where r is actually this x, r is x and e is y, and this
Yes, sir.
you can just relate to this as small m, means slope of the line.
Yes, sir.
This will be like x and this will be like y. That's why, since this graph is actually very similar to y is equal to mx, so we will draw in this way only.
Okay, sir.
I think now you have understood. Now let's end the class.